Today we shall discuss on chapter 5. The title of the chapter is bounded linear operators. Well, if one finds interest in the study of the mathematical objects, we have to deal with a sort of functions or operator or transformations acting on some domain to another domain to define some algebraic structures on such spaces. So, in this case the study of nonlinear space with the linear operators plays a vital role in dealing such objects. So, today we shall discuss on module 1 of this chapter 5. The title of the module 1 is the preliminaries of bounded linear operators on a nonlinear space. Right now we are discussing on module 1 of chapter 5, which is on the some basic results on bounded linear operators. First of all, we recall some preliminaries. Let x and y be two nonlinear spaces over the same scalar field. Here the same notion, that is the norm notion, has been used for norm function. Note that norm function in capital X and y are in general different. So, the definition of a linear operator is such that a function or a mapping or a transformation T from x to y is called a linear operator if number 1 T of x1 plus x2 is equal to T x1 plus T x2 for all x1 x2 belonging to capital X, and number 2 T of alpha x is equal to alpha into T x for all scalars alpha belonging to capital F and for all x belonging to capital X. Hence, capital X is called the domain of T denoted by dt, and T x, the range of x under T, is called the range of T denoted by RT. Now, note that the properties as defined in 1 and 2 are known as additive property for T and absolute homogeneity property for T respectively. The property 1 and 2 can be combined together to a single property, that is T of alpha x plus beta y is equal to alpha T x plus beta T y for all scalars alpha comma beta belonging to capital F and for all x y belonging to capital X. Note that the collection of all linear operators from x to y denoted by curly L x comma y. Now, we take an example. If capital X is equal to capital Y is equal to the space of all reals, that is R, with the Euclidean norm, and define a function T R to R given by T of x is equal to alpha x, where x is taken from R, that is capital R, that is space of reals, and alpha is a fixed real, maybe 0 or maybe non-zero. So, it is easy to verify that T is a linear operator. We take another example. Let T is acting from R2 to R2 defined by T of x comma y is equal to x comma 0 for all x comma y belonging to R2, then it is easy to verify that T is a linear operator. Now, we take a definition. The operator T from x to capital Y defined by T x is equal to 0, that is the 0 element, or we say the 0 vector, sometimes we say the null element, sometimes we say the null vector of capital Y for all x belonging to capital X is called the 0 operator denoted by big theta. The 0 vector of capital X is sometimes denoted by theta x, that is theta subscript capital X. The 0 operator from x to y is always a linear operator. The identity operator, that is the self mapping I from x to x, where I x is equal to x for all x belonging to capital X, is a linear operator. Let us take another example. Let T is a function from C01 to C01, that is C01 is the collection of all real valued continuous functions over the closed interval 01, and it is defined by T of Fs is equal to 0 to 1 kst ft dt, where f is taken from C01 and kst is a real valued continuous function over 0 comma 1 cross 0 comma 1, that is capital Fs is equal to T of Fs, where capital F belongs to C01, s comma t are taken from closed interval 0 1, it is easy to show that t is a linear operator. Let curly Lxy be the collection of all linear operators from x to y. Then curly Lxy is a linear space with respect to the following compositions. For capital T1 comma capital T2 belonging to curly Lxy, define T1 plus T2x is equal to T1x plus T2x for all x belonging to capital X, and for all scalars alpha belonging to capital X, alpha T1x is equal to alpha T1x for all x belonging to capital X. Now we take a theorem. Let capital X and Y be two linear spaces over the same field of scalars capital F, and let T is a mapping or T is a transformation from x to y, that is T x to y is a linear operator which is onto. Then T inverse acting from capital Y to capital X exists if and all if Tx is equal to theta y, which is an element of capital Y, has a unique solution x equal to theta x belonging to capital X. Moreover, T inverse from y to x is again a linear operator. The proof is like this. Let T inverse from y to capital X exist. Now Tx is equal to theta y is equal to T of theta x, because we know that T of theta x is equal to theta y implies x is equal to theta x, because T inverse exists, therefore T is 1 1, and by 1 1 property it implies that x equal to theta x. This shows that x is equal to theta x is a solution of Tx is equal to theta y. If possible, let x1 comma x2, where x2 is different from x1 taken from x, be two solutions of Tx is equal to theta y. So Tx1 is equal to theta y and Tx2 is equal to theta y. So Tx1 is equal to Tx2 implies Tx1 minus Tx2 is equal to theta y, implies T of x1 minus x2 is equal to theta y, because T is a linear operator, which implies that x1 minus x2 is equal to theta x. This implies x1 is equal to x2. So the solution is unique. Conversely, let Tx is equal to theta y has a unique solution x equal to theta x. Let x1 comma x2 belonging to capital X such that Tx1 is equal to Tx2. So Tx1 minus Tx2 is equal to theta y implies T of x1 minus x2 is equal to theta y. This implies x1 minus x2 is equal to theta x. By the given condition, that is Tx is equal to theta y has a unique solution x is equal to theta x. So x1 minus x2 is equal to theta x implies x1 is equal to x2, implying that T is 1 1. Given T is onto, so T is 1 1 and onto, so T is bijective, and hence T inverse is a mapping from y to x exists. Also we know that T inverse is equal to T inverse T is equal to I, the identity operator on x. We shall now show that T inverse from capital Y to capital X is again a linear operator. Let y1 comma y2 belonging to capital Y. So there exists x1 comma x2 belonging to capital X such that T of x1 is equal to y1, T of x2 is equal to y2. Now T inverse y1 plus y2 is equal to T inverse T of x1 plus T of x2, which is equal to T inverse T x1 plus x2 by the property of linearity of T, which is equal to x1 plus x2, again it is equal to T inverse y1 plus T inverse y2. Because Tx1 is equal to y1, that means x1 is equal to T inverse y1. Similarly, x2 is equal to T inverse y2. Similarly, for any alpha belonging to capital F, T inverse alpha y is equal to alpha of T inverse y for all y belonging to capital Y. So T inverse from capital Y to capital X is again a linear operator. Let capital X and capital Y be two nonlinear spaces over the same field of scalars capital F. Now take a definition. A linear operator T from capital X to capital Y is said to be continuous at x naught belonging to capital X if there exists a sequence xn belonging to capital X such that norm of xn minus x naught tends to 0 as n tends to infinity, implies norm of txn minus tx naught tends to 0 as n tends to infinity. That is, xn tends to x naught in x as n tends to infinity, implies txn tends to tx naught in capital Y as n tends to infinity. Equivalently, for any epsilon greater than 0, there exists a delta greater than 0 such that norm of tx minus tx naught less than epsilon whenever norm of x minus x naught less than delta. Now, let us take a theorem. Let T is a linear operator from capital X to capital Y. If T is continuous at one point of capital X, then T is continuous at every other point of capital X. Now, let us take a proof. Suppose capital T is continuous at x naught belonging to capital X. So, given epsilon greater than 0, there is a positive delta such that norm of Tx minus Tx naught less than epsilon whenever norm of x minus x naught less than delta. Suppose x1 be another point of capital X which is not equal to x naught, then if norm of x minus x1 less than delta, we write norm of x minus x1 is equal to norm of x minus x1 plus x naught minus x naught. Thus, norm of x minus x1 less than delta, that is norm of x minus x1 plus x naught minus x naught less than delta, implies by virtue of continuity of capital T, we get norm of T of x minus x1 plus x naught minus T of x naught is less than epsilon, or norm of Tx minus Tx1 plus Tx naught minus Tx naught less than epsilon by the property of linearity of capital T. So, which is equivalent to norm of Tx minus Tx1 is less than epsilon. This implies that T is continuous at x equal to x1. Now, let us take a corollary. A linear operator over a nonlinear space capital X is continuous either everywhere or nowhere in capital. Let us take another definition. A linear operator T from capital X to capital Y is called bounded if there exists a positive constant capital M such that norm of Tx less or equals to m into norm of x for all x belonging to capital X. In other words, norm of Tx divided by norm of x less or equals to capital M for all non-zero member x belonging to capital X. The lower bound of all members capital M greater than 0 for which norm of Tx less or equals to m into norm of x for all x belongs to capital X is called the norm of the operator T and denoted by norm T. Now, let us take a theorem. Let T is a mapping from capital X to capital Y be a bounded linear operator. Then number 1, norm of Tx less or equals to norm of T into norm of x for all x belongs to capital X, and number 2, norm of T equal to supremum of norm of Tx where supremum is taken over norm of x less or equals to 1. So, we shall take a proof one by one. For the proof of 1, let us take an epsilon greater than 0 which is arbitrary. So, it follows by definition that norm of Tx is less or equals to norm T plus epsilon into norm of x for all x belonging to capital X. If possible, let there exist x1 belonging to capital X such that norm of Tx1 is strictly greater than norm of T into norm of x1. Then for some epsilon greater than 0, norm of Tx1 greater than norm of T into norm of x1 plus epsilon into norm of x1, which is equal to norm T plus epsilon within a bracket into norm of x1, which contradicts 1, hence norm of Tx is less or equals to norm T into norm of x. Let us take a proof for 2. If norm of x less or equals to 1, then norm of Tx less or equals to norm T into norm of x, which is less or equals to norm T because norm of x less or equals to 1. And so, supremum of norm of Tx where supremum is taken over norm of x less or equals to 1, and this is less or equals to norm of T. On the other hand, by definition, for every epsilon greater than 0, there exists x dash which is not equal to theta such that norm of Tx dash greater than norm of T minus epsilon into norm of x dash. Let x1 is equal to x dash by norm of x dash. Then we have norm of Tx1 is equal to 1 by norm of x dash into norm of Tx dash, which is greater than 1 by norm of x dash into norm of T minus epsilon within the bracket into norm of x dash, which is equal to norm T minus epsilon. Since norm of x1 is equal to 1, we get supremum of norm of Tx where supremum is taken over norm of x less or equals to 1 is strictly greater or equals to norm of Tx1 and greater than norm of T minus epsilon. And since epsilon greater than 0 is arbitrary, we have supremum of norm of Tx where supremum is taken over norm of x less or equals to 1 and it is greater or equals to norm of T. So, combining the earlier results, we get supremum of norm of Tx where supremum is taken over norm of x less or equals to 1 is equal to norm t. Now here we shall use some notation, collection of all bounded linear operators from a non-linear space capital X to another non-linear space capital Y and denoted by BD curly LXY, that is collection of all bounded linear operators from X to Y. Let us take an example. Let T is a mapping from R2 to R2 which is defined by T of xy is equal to x dash comma y dash, where x dash is equal to x cos theta plus y sin theta, y dash is equal to minus x sin theta plus y cos theta, and the norm on R2 is given by norm of x comma y is equal to root over x square plus y square, where x comma y is taken from R2. It can be easily verified that T is a linear operator. Now norm of T of x comma y whole square is equal to norm of x dash comma y dash square is equal to x dash square plus y dash square is equal to x square plus y square, which is equal to norm of x comma y whole square. So T of xy is equal to norm of x comma y, which is less or equals to k into norm of xy if k greater or equals to 1. So T is bounded and hence T is continuous on R2. Consider the Banach space C01, the space of all real valued continuous functions over 01 with respect to the sup norm, that is norm of f is equal to supremum of mod of ft, where 0 is less or equals to t less or equals to 1, that is supremum is taken over the closed interval 0 comma 1 and f is taken from C01. Let kst be a real valued continuous function over 0 comma 1 cross 0 comma 1. So kst is bounded over 0 comma 1 cross 0 comma 1. Let capital M is equal to supremum of modulus of kst, where supremum is taken over 0 comma 1 cross 0 comma 1. Now define a mapping T from C01 to C01 by T of f is equal to capital F, where capital Fs is equal to integration 0 to 1 kst ft dt, where f is taken from C01. Clearly capital F is continuous over 0 comma 1. Now norm of Tf is equal to norm of f is equal to supremum of modulus of Fs, where supremum is taken over closed interval 0 comma 1, which is equal to supremum of 0 less or equals to t less or equals to 1 modulus of integration 0 to 1 kst ft dt, which is less or equals to supremum over 0 less or equals to t less or equals to 1 integration 0 to 1 modulus of kst into modulus of ft dt, which is less or equals to capital M into integration 0 to 1 mod of ft dt, which is less or equals to capital M into supremum of 0 less or t less or equals to 1 modulus of ft into integration 0 to 1 dt, which is equal to capital M into norm of f. This is true for every member f belonging to C01. So T is shown to be bounded. Let us take another example. Let C101 denote the class of all real valued continuous functions that are continuously differentiable over 01. Then C101 is a subspace of C01, which is again a Banach space with respect to sup norm. Consider the differential operator T from C101 to C01 by T of f is equal to f dash, where f dash is the differentiation of small f, where f is taken from C101. We can easily verify that capital T is a linear operator, but capital T is not bounded. Let us take Fn belongs to C101 by Fnt is equal to sin n pi t, where 0 less equals to t less or equals to 1. Clearly Fnt are differentiable. So T of Fn is equal to Fn dash, where Fn dash t is equal to n pi cos n pi t, where 0 less or equals to t less or equals to 1. Now norm of Fn is equal to supremum of modulus of sin n pi t, and supremum is taken over the closed interval 0 1 and which is equal to 1, but norm of Tfn is equal to norm of Fn dash is equal to supremum of modulus of n pi cos n pi t, and supremum is taken over the closed interval 0 1, which is equal to n pi and tends to infinity as n tends to infinity. This implies that capital T is not bounded. Let us take a theorem. Let capital X and capital Y be two non-linear spaces over the same field of scalars capital F, and let T is a mapping from capital X to Y which is linear. Then T is continuous if and only if capital T is bounded. Let us take a proof. Let T is a bounded linear operator from capital X to capital Y. So, there exists a constant k greater than 0 such that norm of Tx less or equals to k into norm of x for all x belonging to capital X. Let xn be a sequence of elements in capital X such that xn goes to x as n tends to infinity, that is norm of xn minus x tends to 0 as n tends to infinity. Now, norm of Txn minus Tx, which is equal to norm of Txn minus x by the linearity of capital T, and which is less or equals to k into norm of xn minus x and tends to 0 as n tends to infinity. So, norm of Txn minus Tx tends to 0 as n tends to infinity, that is Txn goes to Tx as n tends to infinity, implying that T is continuous. Again, let capital T is continuous. So, we have to prove that capital T is bounded. If possible, let T is not bounded. So, for every n we can find xn which is not equal to 0 vector of capital X such that norm of Tx is greater than n into norm of xn. Let un is equal to xn by n into norm of xn, which is an element of capital X. So, norm of un is equal to 1 by n, and which goes to 0 as n tends to infinity, and this implies un goes to 0 vector of capital X as n tends to infinity as T is continuous. Now, T of un goes to T of theta x is equal to theta y as n tends to infinity. Again, norm of T un is equal to norm of T of xn by n into norm of xn, because un is equal to xn by n into norm of xn is equal to 1 by n into norm of xn into T of xn is equal to 1 by n into norm of xn into norm of Txn is greater than n into norm of xn by n into norm of xn is equal to 1, that is norm of Tun greater than 1. So, limit n tends to infinity, norm of Tun is greater or equals to 1, which is not possible, hence T is bounded. Up to this we have learned some basic definitions with some preliminaries and with some examples, that is when a bounded linear operator is continuous. Now, we shall now show some equivalent properties of continuity of a linear operator with the properties of boundedness. Now, let us take a theorem. Let capital X and capital Y be two nonlinear spaces over the same field of scalars capital F, and let T is a linear operator from capital X to capital Y. Then the following statements are equivalent. Number 1, capital T is continuous. Number 2, capital T is continuous at 0 vector of x. Number 3, there exists a constant m greater than 0 such that norm of Tx less or equals to m into norm of x for all x belonging to capital X. Number 4, capital T is uniformly continuous. Number 5, if capital S is equal to collection of all elements x belonging to capital X such that norm of x less or equals to 1, then T of capital S is bounded in capital Y. The proof goes below. 4 implies 1 implies 2, which is very trivial. Now, 2 implies 3. Let 2 holds. Let us suppose that 3 do not hold. So, for every positive integer k, there exists xk which is not equal to 0 vector of capital X such that norm of Txk greater than k square into norm of xk. Let yk equal to xk divided by k into norm of xk. So, norm of yk is equal to 1 by k, which goes to 0 as k tends to infinity. This implies that yk goes to 0 vector of capital X. As T is continuous at 0 vector belonging to capital X, T of yk goes to T of 0 vector, which is equal to 0 vector of capital Y. Now, norm of Tyk is equal to norm of T of xk by k into norm of xk is equal to 1 by k into norm of xk into norm of Txk, which is again greater than 1 by k into norm of xk into k square into norm of xk, which is equal to k and greater than 0, which is not possible as T of yk goes to 0 vector in capital Y. So, 3 holds. Now, 3 implies 4. Let 3 holds. Let epsilon greater than 0 be arbitrary. Choose delta is equal to epsilon by capital M plus 1, which is greater than 0. Let x comma y belonging to capital X such that norm of x minus y is strictly less than delta. Now, norm of Tx minus Ty is equal to norm of T of x minus y, which is less or equals to capital M into norm of x minus y, which is less or equals to m into delta is equal to m into epsilon by m plus 1, which is strictly less than epsilon. So, T is uniformly continuous. Now 3 implies 5. Let 3 holds. Let x belonging to capital X, so norm of x less or equals to 1, but norm of Tx less or equals to m into norm of x by 3, which is less or equals to capital M. Thus, for all x belonging to capital S, norm of Tx less or equals to capital M implies T of capital S is bounded in capital Y. Now 5 implies 3. Let 5 holds. Let x is an element belonging to capital X, which is not equal to 0 vector of capital X. Take y is equal to x by norm of x. So norm of y is equal to 1. So y belonging to capital S. So there exists a capital M greater than 0 such that norm of Ty less or equals to capital M. Show 3 holds. Let us take a theorem. Let capital X be a finite dimensional nonlinear space over a field capital F, and capital Y be a nonlinear space over the same field of scalars capital F. Suppose that T from capital X to capital Y be a linear operator, then capital T is continuous, or rather it is T is bounded on capital X. Now let us take a proof. Let dimension of x is equal to n, say. Let E1, E2, En be a basis of capital X. Let x belonging to capital X. Then x is equal to alpha 1 E1 plus alpha 2 E2 plus dot 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 plus alpha n En, where alpha 1, alpha 2, alpha n belonging to capital F. Hence, there exists a constant c greater than 0 such that norm of x greater or equals to c times sigma I equal to 1 to n modulus of alpha I. So norm of Tx is equal to norm of sigma I equal to 1 to n T of alpha I Ei, which is less or equals to sigma I equal to 1 to n modulus of alpha I into norm of T Ei, which is less or equals to capital M into sigma I equal to 1 to n modulus of alpha I, where capital M is equal to maximum of 1 less or equals to I less or equals to n collection of all such elements norm of Ti, which is greater or equals to 0, and m into sigma I equal to 1 to n modulus of alpha I less or equals to m by c into norm of x, which is equal to k into norm of x, where k is equal to capital M by c, which is greater or equals to 0. Thus, norm of Tx less or equals to k into norm of x, where k is strictly greater than 0. So T is bounded. Let us take a theorem. Let capital X and capital Y be two nonlinear spaces over the same field of scalars capital F. Let BD_LXY denote the class of all bounded linear operators from capital X to capital Y. Then BD_LXY is a nonlinear space with respect to the norm defined by norm of T equal to supremum of norm of Tx, and supremum is taken over norm of x less or equals to 1, and x is taken from capital X and T is taken from BD_LXY. Proof. Given norm of T is equal to supremum of norm of Tx, where supremum is taken over norm of x less or equals to 1, clearly norm of T is greater or equals to 0. Now norm of T equal to 0 implies supremum of norm of Tx, where supremum is taken over norm of x less or equals to 1, which is equal to 0. Thus, for x belonging to capital X with norm of x less or equals to 1, norm of Tx is equal to 0, which implies that Tx is equal to theta y for all x belonging to capital X with norm of x less or equals to 1. Let norm of x is equal to alpha greater than 1. Take y is equal to x by beta, where beta is greater than alpha, that is strictly greater than alpha. So norm of y is equal to norm of x by beta is equal to 1 by beta into norm of x is equal to alpha by beta, and which is strictly less than 1. So norm of y less than 1 implies Ty is equal to theta y, which implies that T of x by beta is equal to theta y, that is the 0 vector of capital Y, which implies that Tx is equal to beta into theta y is equal to theta y for all x belonging to capital X wherever norm of x is greater than 1. From the earlier results, for all x belonging to capital X, we get Tx is equal to theta y. So T is a 0 operator. So norm of T is equal to big theta, which implies that T is a 0 operator. Also, if T is equal to 0 operator, then norm of T equal to 0 always. So first condition of norm, that is the norm axiom 1, is satisfied. If alpha belonging to capital F, we have norm of alpha t is equal to supremum of alpha Tx, where supremum is taken over norm of x less or equals to 1 is equal to supremum of alpha into Tx, where supremum is taken over norm of x less or equals to 1, which is equal to supremum of mod of alpha into norm of Tx and norm of x less or equals to 1 for which supremum is taken is equal to modulus of alpha into supremum of norm of Tx, where supremum is taken over norm of x less or equals to 1, which is again equal to modulus of alpha into norm of T. So, the second norm axiom, that is N2 axiom, is satisfied. Now, norm of T1 plus T2 is equal to supremum of T1 plus T2x, and supremum is taken over norm of x less or equals to 1, which is equal to supremum of norm of T1x plus T2x, where supremum is taken over norm of x less or equals to 1, which is again less or equals to supremum of norm of T1x, where supremum is taken over norm of x less or equals to 1 plus supremum of norm of T2x, and supremum is taken over norm of x less or equals to 1, which is again equals to norm of T1 plus norm of T2. So, third norm axiom, that is N3 axiom, is satisfied. Thus, all the norm axioms are satisfied, and hence BDLXY is a nonlinear space. Let capital X and capital Y be two nonlinear spaces over the same field of scalars capital F, in which capital Y is complete. Then BDLXY is a Banach space. The proof goes below. Let sequence Tn is taken from BDLXY, which is supposed to be a Cauchy sequence. So, norm of Tn minus Tm tends to 0 as n comma m tends to infinity. So, for each x belonging to capital X, norm of Tnx minus Tmx is equal to norm of Tn minus Tm of x, which is again less or equals to norm of Tn minus Tm into norm of x, which goes to 0 as n comma m tends to infinity. So, Tnx is a Cauchy sequence in capital Y. Since capital Y is complete, so limit of n Tnx is equal to y belonging to capital Y, y is dependent on x. So, let us define a map T from x to y by Tx is equal to y. So, limit of n Tnx is equal to Tx. Clearly, T is linear. Now, modulus of norm of Tn minus norm of Tm is less or equals to norm of Tn minus Tm tends to 0 as n comma m tends to infinity. So, norm of Tn is a Cauchy sequence of real scalars. So, set of all norm of Tn is a Cauchy sequence of real scalars. So, there exists a constant k greater than 0 such that norm of Tn less or equals to k for all n. So, norm of Tx is equal to norm of limit of n Tnx, which is equal to limit of n norm of Tnx, because norm function is continuous, which is again less or equals to limit of n norm of Tn into norm of x, because Tn is taken from BDLXY, which is less or equals to k into norm of x. This implies that capital T is bounded on x, and hence T belongs to BDLXY. As Tnx is a Cauchy sequence in capital Y, so for every epsilon greater than 0, there exists a positive integer capital N such that Tnx minus Tn plus Px less than epsilon whenever n greater or equals to capital N and p equal to 1, 2, 3 and so on. Now, letting p tends to infinity, norm of Tnx minus Tx is strictly less than epsilon whenever n is greater or equals to capital N. So, norm of Tn minus T is equal to supremum of norm of Tn minus Tx, and supremum is taken over norm of x less or equals to 1 is equal to supremum of norm of Tnx minus Tx, and supremum is taken over norm of x less or equals to 1, which is again less or equals to epsilon whenever n is greater or equals to capital N. That is, norm of Tn minus T less or equals to epsilon whenever n greater or equals to capital N, which implies that Tn goes to capital T as n tends to infinity. So, BDLXY is complete, and hence BDLXY is a Banach space. In this module, we have learnt some basic results on bounded linear operators. Also, we have established some results on continuity of a linear operators.